Are you curious about the building blocks of all matter? Look no further than the periodic table of elements. The periodic table is one of the most important tools in chemistry, as it categorizes all known elements based on their properties and behavior. In this video, we'll explore the structure of the periodic table, how it is organized, trends displayed by the periodic table, and why it is important. The periodic table is a tabular arrangement of elements based on their atomic number, electronic configuration, and chemical properties. Each element is featured as a block, and the elements are arranged in vertical columns called groups and horizontal rows called periods. Elements in the same group or period have similar properties. A zigzag line can be found on modern periodic tables which separate the metals and nonmetals. Metals are found to the left of this line, while nonmetals are to the right. Metals are generally shiny, malleable, ductile, and good conductors of heat and electricity, while nonmetals are usually dull and brittle and are poor conductors. The periodic table is based on the atomic structure of elements. Each element has a unique number of protons, neutrons, and electrons, which determines its position on the table. Zooming into the periodic table, we notice that each block contains an atomic number, which is the number of protons in the atom, the chemical symbol of the element, which is a 1 or 2-letter abbreviation of the element name, and the mass number, which is the total number of protons and neutrons in the nucleus of the atom. In addition, some periodic tables may include the chemical name, melting and boiling points, electronegativity of the element, and so forth. The periodic table is arranged in order of increasing atomic number, starting with the element that has the atomic number of 1, which is hydrogen, moving on to helium with an atomic number of 2, then to lithium with an atomic number of 3, and so forth. The atomic numbers increase from left to right across the rows of the periodic table. The periodic table exhibits periodic trends, which are patterns in the properties of elements as you move across a period or down a group of the table. One such trend is the atomic radius, which refers to the distance from the nucleus to the outermost electron shell. The atomic radius decreases as you move from left to right across a period. This is because as you go across a period, electrons are added to the same energy level. At the same time, protons are being added to the nucleus, which creates a stronger force of attraction. This pulls the electrons closer to the nucleus, resulting in a smaller atomic radius. The atomic radius increases as you move down a group. This is because the number of electrons and energy levels increase as you move down a group. Each additional energy level is further from the nucleus than the previous. Hence, the atomic radius gets larger down the group. Another trend is electronegativity, which refers to the tendency of an atom to attract electrons to itself in a chemical bond. Electronegativity increases as you move from left to right across a period and decreases as you move down a group. Another trend is that as we move from left to right across a period, we move from metals to semi-metals to nonmetals. The groups are numbered from left to right. Some periodic tables are numbered from 1 to 18, while others are numbered from 1A to 8A, leaving the middle groups unnumbered. The last group, Group 18 or Group 8A, is also numbered as Group 0 on some periodic tables. We will be using the later numbering system in this video. The group number represents the number of valence electrons of the elements. Valence electrons are the electrons found on the outermost shell of an atom. Elements in the same group have the same number of valence electrons. For example, Group 1 elements have 1 valence electron, Group 2 elements have 2 valence electrons, etc. This is a reason why elements in the same group share similar chemical properties and bond to other elements in a similar way. Group 1 elements include hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Group 1 elements are highly reactive due to their single valence electron. They readily lose this electron to form positive ions. As we move down the group, reactivity increases because the outermost electron is further from the nucleus and more easily lost. Group 1 elements, except for hydrogen, are called alkali metals. This is due to the formation of alkali solutions upon the reaction with water. Alkali metals are relatively soft silvery white metals with low melting points. Hydrogen is a colorless, odorless, tasteless, non-toxic, and highly combustible gas. This is a reason why hydrogen is separated from the group 1 elements in some periodic tables. Group 2 elements include beryllium, magnesium, calcium, strontium, barium, and radium. They are known as the alkaline earth metals and are harder and denser than alkali metals and have higher melting points. They have 2 valence electrons and are less reactive than alkali metals, but still form positive ions by losing their valence electrons. Reactivity increases as we move down the group for the same reason as the alkali metals. The transition metals are found in the middle of the periodic table between groups 2 and 3. They are metals of high density with high melting and boiling points. They form colored compounds. They are used in various fields such as medicine, construction, and energy due to their properties of malleability and ductility. They are often used in industries as catalysts for various reactions. Iron mixed with manganese and chromium gives steel. Steel is used for construction purposes, building cars and aircraft. Nickel is used in producing stainless steel. Copper is used for electrical wiring. Transition metals are also essential for biological functions. Iron is used in our body to create hemoglobin, which is used to carry oxygen in the blood, and not enough iron in our blood can cause anemia. At the bottom of the periodic table, we find lanthanides and actinides. They are also transitional metals with atomic numbers of 57 to 71 for the lanthanides and 89 to 103 for the actinides. The lanthanides include the metals lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. The lanthanides are silvery white metals with high melting and boiling points. They are radioactive metals except for promethium. The actinides include actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. They are all radioactive, soft silvery white metals. Uranium and plutonium are used in nuclear fuels and weaponry. Along the zigzag line that separates the metals and nonmetals, we find the metalloids. A metalloid or semimetal is an element that has properties that are intermediate between those of metals and nonmetals. They include boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. They typically have metallic appearances, but are brittle and are only fair conductors of heat and electricity. The semiconductivity is a reason why silicon is used in computer chips. The nonmetals are found on the right side of the periodic, except for hydrogen, which is often found in group 1. The nonmetals include hydrogen, carbon, nitrogen, oxygen, phosphorus, sulfur, selenium, the halogens, and the noble gases. Nonmetals typically have low melting and boiling points, do not conduct electricity, and can be found in either gas, liquid, or solid states. Halogens are found in group 7 and are highly reactive nonmetals. These are fluorine, chlorine, bromine, iodine, astatine, and tennessine. Halogens all exist as diatomic molecules, meaning they are composed of 2 atoms. In this case, they are composed of 2 of the same elements and are therefore said to be homonuclear. They have 7 valence electrons and readily gain 1 electron to achieve a stable electron configuration. Reactivity decreases as we move down the group due to the increasing atomic radius and decreasing electron affinity. When a more reactive halogen reacts with a less reactive halide, a displacement reaction occurs as one atom replaces another. For example, for the reaction between chlorine and potassium bromide, chlorine is more reactive than bromine from the potassium bromide and takes its place. Yet, bromine would not displace chlorine in a similar reaction, as bromine is less reactive than chlorine. The noble gases are located in group 8, which is sometimes also referred to as group 0. These are helium, neon, argon, krypton, xenon, radon, and oganesson. They have full valence electron shells and are therefore unreactive. They are colorless gases with low boiling points. Density and boiling point increase down the group. Because noble gases are unreactive and can therefore be used in the following ways. Helium, being of very low density, is used to fill balloons. Neon is used in advertising sign lighting since neon has a glow when electricity passes through it. Argon is used to fill electric light bulbs so that the gas inside the light bulb does not ignite. Krypton is used in lasers for eye surgery and also in car headlamps. We now focus on the remaining metals: aluminium, gallium, indium, thallium, nihonium, tin, lead, fluorovium, bismuth, moscovium, and livermorium. Each of these metals possesses unique properties and characteristics that make them valuable in various fields of science, industry, and technology. Gallium, for instance, is a soft, silvery metal with a melting point slightly above room temperature. Its remarkable ability to liquefy in one's hand owing to its low melting point makes it notable. Gallium finds extensive usage in electronics, semiconductor production, and as a constituent in certain medical imaging devices. To sum up, the periodic table is a great tool for understanding the properties and behavior of elements. It provides an orderly way of organizing elements and has been instrumental in advancing our understanding of chemistry and the natural world. From the discovery of new elements to the development of new materials, the periodic table continues to play a vital role in scientific research and innovation. So, the periodic table is a fascinating subject that is worth exploring further. Thank you for watching, and I hope you enjoyed this tour of the periodic table and learned a lot. Be sure to give it a thumbs up and subscribe for more fascinating chemistry videos.